Hey everyone, welcome to the Cerebras podcast. I'm James Wang, Senior Product Marketing Manager here, running our podcast program. Today, I have the pleasure of speaking with Vithu Thangarasa, who is a senior research scientist working on our sparsity effort. And he recently published a paper with some great research insights into the sparsity. We want to get into the whole background of what sparsity is in neural networks, why you do it, kind of where the state of the art is, and what this paper covers. Vithu, welcome to the podcast.
Thanks, James. Thanks for having me here. I look forward to our chat and hopefully I can share some of my insights and some of the things I've gained over the years on sparsity.
Let's start with sparsity. I mean, I think everyone knows neural networks, what they are, and transformers. I guess by default in the industry, we call them dense. And you're doing research on sparse neural networks. So what is what is meant by dense? What is meant by sparse? And why are we interested in sparsity?
Yeah, I think that's a great question. And first of all, dense matrices are basically all the weights in a matrix when you're doing, like, for example, a fully connected layer, matrix multiplication, they're non-zero. But whereas in a sparse matrix, you have zero elements within your matrix. So when you do sparse matrix multiplication, if you have hardware that can actually support accelerating these sparse matrices, you can get computational speedup by not doing compute on these zero elements. So this is why sparsity provides a huge advantage over dense matrix multiplication. And
Like saving you wasted work.
Yeah, exactly. And by reducing the number of these the number of active computations, sparse models can basically lead to these speedups, which is super important for the scale of models that we train with these days.
Right. When you work on the model weights, are they zero by default? Like when you train them, what do the typical range of values look like, and when is it safe to sparsify the model, so to speak, set weights to zero?
Yeah, so I mean, there's different ways to impose sparsity, and sometimes you have naturally occurring weight sparsity, for example, due to the activations that we use in the architecture and the data set, which contributes to sparse weights naturally during the optimization process. But then there are other ways as well, like we can induce regularization into the training itself. So sparsity can basically, you can drive certain weights to zeros by imposing like a regularizer on the weights. And the kind of disadvantage with this is you can't necessarily control the amount of sparsity that you want to achieve, like, for example, a certain speed up. Whereas more modern sparsity research focuses on more hard level like sparsity limits or targets. For example, if you target 80%, you can specify like randomly or through some sort of distribution that 80% of the weights in a particular layer are set to zero. And so this is how a lot of the research these days on sparsity tend to achieve flop reduction in neural networks.
Is that safe to do? I mean, in normal training, you're just doing math like by the book. And now we're going to set 80% of weights to zero. That's a huge change over the standard protocol. Like, I guess from the theoretical perspective, why is it okay to do that?
Yeah, so I think this is one of the hypotheses we actually had. So when we started the sparsity research, a lot of the intuition kind of came from, training these sparse models and then comparing it to dense models. We're using the same exact setup as dense training, but then we're now, like I described, we're inducing manually sparsity into the weights, right? And so depending on the task, what we found was, depending on the task, certain and the size of the model, you can induce different degrees of weight sparsity. For example, if you have a smaller architecture, but a much more difficult task, it's much more difficult to induce weight sparsity into that model. Whereas if you have a larger architecture, which has significantly more parameters, but then the task is easy, then you have a lot of room to induce sparsity and still have negligible performance loss on the actual task itself. So it's like it's something you have to balance, like depending on the size of the model, the difficulty of the task, it can kind of dictate how much sparsity you can induce into the model training itself. But
in
this
way,
kind of, yeah,
I guess in this way, large language models are particularly beneficial for as a recipient of sparsity, because they are already so humongous, upward of 200 billion parameters. I guess the thinking is that probably you don't need every parameter there to be like non-zero to express the value and the functionality in the model. So it's like more compressible by sparsity.
Yeah, I think yeah, this kind of goes back to some of the work we've done as well internally, where in the beginning we would like try these algorithms with like sparse algorithms on computer vision models, and then try to hopefully transfer those findings towards transformer models or like large language models. But we quickly realized that it doesn't necessarily work that way. And sparsity in transformers, particularly in the context of large language models, such as BERT, GPT, it's actually a lot more difficult to sparsify language models. And this is an active area of research, and new techniques and insights continue to emerge. But there's a lot of things that we discovered in the process, and it actually is out there on existing literature as well. Like, for example, redundancy in attention heads. So transformers typically consists of these multiple attention heads, but some attention heads in a transformer may be redundant or less informative. So removing these or like inducing sparsity into these can reduce the compute requirements without actually having a significant performance degradation. And there's a trade-off between the sparsity and performance. So achieving high levels of sparsity in transformers while maintaining a performance is actually pretty delicate trade-off. And this is one of the things that we explored in our recent work that was presented at the iClear sparsity workshop.
Okay, so let's talk about your paper. I understand every year there's an iClear sparsity workshop. Is this kind of where the central, I don't know, venue where researchers around the world present on sparsity? Because I feel like sparsity is still one of these emerging areas in ML. It's not in the standard production. It's kind of on the frontiers of research, coming into production. What was the key takeaway from your paper? What was the name of the paper, and what's the key takeaway?
So the title of our paper was Sparse Pre-training and Dense Fine-tuning for Large Language Models. The main sort of driving motivator for that work was the amount of compute required to pre-train these large language models, super expensive, right? And it's not very easy to induce sparsity naively into transformers, because there's always like a performance loss when you evaluate on the downstream tasks that you're interested in. So, and it's quite established that you typically pre-train a large language model and then you evaluate on some generic downstream tests. So we decided to decouple the two things and show that we can actually significantly reduce the amount of computational requirement during the pre-training phase, but then during the fine-tuning phase, we can recover the lost performance or like the lost representational power during pre-training by doing dense fine-tuning. So we induce sparsity during the pre-training phase to get our flop reduction and training time speed up. And then during the fine-tuning phase, we'll do dense fine-tuning, which essentially means you allow those zeroed weights from sparsity to learn, and they become learnable parameters. So now you effectively have that original dense model during the fine-tuning phase. But since fine-tuning is so, the amount of compute required to fine-tune is so insignificant compared to the pre-training, we're okay with doing this dense fine-tuning step because it does allow the model to recover a lot of the performance drop.
I see. So typically 99% of the training, the compute cost is in pre-training. In that very expensive phase, you sparsify the training process. You lose some perf on, I guess, pre-trained test loss, but you've fine-tuned using the full dense matrix and then basically recover that performance. It seems like some magic mojo there. You're having your lunch, and eating it too. What is the theoretical basis of why this would even work? How can it recover? I guess to be able to recover the performance in a way, it must have not been lost in the pre-training phase to begin with, right? Like, how do you think about it theoretically?
Yeah, actually, there were three hypotheses that we studied in this paper, and one of them was we can which was the first thing I mentioned, which was we can do dense fine-tuning and induce weight sparsity, high degrees of weight sparsity in the pre-training phase, but still be able to recover performance. But then the second hypothesis was the performance of this sparse pre-trained model is now correlated with the data set size and the degree of difficulty in the downstream task. So it's not that we can consistently do dense fine-tuning and always recover the performance, because depending on the size of the model and the data set size that you're using for fine-tuning, it can be difficult to recover the performance. Or if it's like the size of the model increases, then it becomes more easier to induce high levels of sparsity during pre-training and recover the performance. So that was the third hypothesis. Like, as the size of the model increase, it becomes more amenable to high levels of sparsity and during pre-training. And to answer your question, we actually studied the parameter subspaces of the pre-trained model. So we looked at all the layers across the depth of the network, including the attention matrices and then the feed-forward layers. And then we compared against the parameter subspace of the fine-tuned model. And we analyzed how much change happened between the two parts of training. And you see that in smaller large language models, there's a lot more change in the actual parameters in certain layers of the network versus larger language models, where only maybe a few layers actually undergo any sort of significant change compared to its like the fine-tuned model, which kind of says that, these large models encode much more rich information due to the higher parameter size or parameter count. They have more, I guess, representational power to encode a lot of these information, whereas these smaller models kind of struggle to generalize across many NLP tasks on the downstream side.
When you say the change, what is the change with respect to?
Right. So it's the weights themselves. So the weights of the large language model during pre-training. For example, you take like a particular layer, and then we compute the distance between the same layer, but after fine-tuning. So at the end of pre-training and then the end of fine-tuning, and we compare how much change that particular layer underwent. And we see that, like I said, like the larger model tends to undergo very minimal change. And it was just a way to sort of provide some interpretability into why we can actually do this sparse pre-training and dense fine-tuning and kind of get away with it, right? As such a simple technique.
So what were the results like? I mean, how much performance would you have nominally lost after the pre-training phase, and what did the fine-tuning recover?
Right. So there were two setups that we evaluated. Obviously, the logical baseline would be you do a sparse pre-training run and then you do a sparse fine-tuning run, right? And then we compared it against our proposed method, which is sparse pre-training followed by dense fine-tuning. And you see that we have some plots in the paper where we show as you increase the sparsity level, there's quite a significant drop if you do sparse pre-training followed by sparse fine-tuning, which is like sparse to sparse training.
How
But
much
then when you
drop?
do this,
Yeah.
when you do this sparse to dense training,
Yeah.
we close the gap significantly compared to the dense baseline. And so the tasks that we evaluated on were natural language generation tasks, and text summarization. So these are well-established tasks in the NLP literature for GPT models. And so we try to make it consistent with some of the earlier works, for a better comparison against models that earlier works have also trained. And we can push sparsity up to actually 75% in like a GPT-3 1.3 billion parameter model, which is a significant number of weight reduction during training. So this is I think one step in this direction towards reducing compute time during pre-training of large language models.
That's amazing. Okay, so this paper has demonstrated you can kind of get the bulk of the performance benefit of sparse training a large language model, and not and still maintain the actual downstream task accuracy without trading off just a tiny smidgen by the end. What I guess this, I think, gets us most of the way there. Right now, I guess large language models in the applications that are popular today are still dense. How far does this get? How far does this get us into a production workflow or recipe for, a mainstream LLM? And what do you think needs to happen still before someone the likes of OpenAI or Anthropic would consider using sparse as kind of a real approach that someone could use in production?
Yeah, I think that's a great question. There's definitely I guess mixed views on this, and I think personally, depending on your I think it all depends on what your application is. So maybe you can train a model, a sparse model, right? And you have the hardware that supports it, supports sparse training. Maybe you can train a sparse model much for a shorter time and get negligible performance drop, or there might be some performance drop, but you're okay with it because you're able to deploy this model now on like research constrained hardware, or you're okay with like maybe taking a small performance hit because it gives you such a significant savings on the compute time, right? So maybe in another application, accuracy is the biggest deciding factor. So you don't want to sacrifice any accuracy. So you may want to train dense, or maybe like some moderate level of sparsity, which can give you some training time reduction, but also maintain the accuracy. So I think there's trade-offs here. If companies do want to train sparse networks, I think it'll all definitely just come down to the actual application.
Mm-hmm. If you're an ML developer, app developer, and you're considering different recipes, large dense, large sparse, medium dense, medium sparse, things like that, knowing what you know from this research, I guess what recipe of size and sparsity and data, I guess, would you be inclined to explore as your baseline?
Yeah, definitely. So I think the first thing obviously is try to test out what's the best you can do with just pure sparse training, right? And how does the model perform on whatever application that we're trying to use that model for? And then say if say if it does not as well, now you can do other techniques. Like there's been some works where they explore like switching from sparse to dense in the actual pre-training phase. So you can actually recover some of the lost representational power on the pre-training itself, and then that can be used. Now you end up with some dense model at the end, right? And that can be used for your application or your fine-tuning or zero shot, whatever it may be. But yeah, you can play around with sparsity. You don't have to use sparsity like constant throughout the whole training period. You can choose, I guess, when to use it, and that's an open area research of like when to induce what amount of sparsity during training.
Mm-hmm.
And as I think like depending on the size of the model, this is going to change, and it's not like a sort of like a recipe, like one recipe for a generic set of architectures, but it will be again like model dependent, size of the model, data sets that you're training on, and because of how long these pre-training runs take, we generally don't do like hyperparameter tuning on the sparse models,
I see.
because we typically just take the same hyperparameter configs as the dense model and then use it for the sparse model, and try to kind of get it to still work. But maybe there's optimal hyperparameter configs that exist for sparse training that we just haven't like discovered, and for dense models it's already well established. So I think there's a multitude of things that we'd have to consider if we're giving like some sort of like handbook for sparse training.
Right. Most of the sparsity research, I guess, in the last decade or so has focused on using this for vision models like image convolutional neural networks.
Right.
Do you feel, and that's had been more successful there because, like, I guess it's easier to set weights to zero. Do you feel like right now we're at the point where for transformers we are, have we reached the same level of success, or there's still some ways to go?
I think, yeah, you're right. That, well, it's true that most of the sparsity research has focused on computer vision models. Like sparsity goes back all the way to 1980s, and then it recently got picked up one in the 2010s, like under the umbrella of pruning. So you're trying to target cost reduction during inference time. And then it kind of got renewed by the lottery ticket hypothesis, which was proposed by Jonathan Frankel and Michael Carbon at MIT. And a lot of the work has, focused on computer vision models because they're more over parameterized, and they tend to be evaluated on C400 and ImageNet. But now we're starting to see a lot more work on language models and sparsity, like BERT and GPT for training time, speed up or inference. But I think sparsity in transformers, particularly in the context of large-scale models such as BERT or GPT, is still an active area of research. While there are some works that are starting to come out, we have gained a lot of insights in transformers, I think, in terms of understanding the behavior of attention heads, mechanisms for pruning and adding regularization for architectural modifications of transformers. I think, and sparse training itself. So using like dynamic sparse training, or different kind of, I guess, sparse updates to handle some of the challenges that are posed by transformers. So I think the community itself is still like investigating different techniques, and it's kind of like branched out in different, I guess, categories or groups, but we don't have this kind of same sort of unified approach that we do see in like computer vision models. And I think going forward, that's going to change. I mean, I think there's in particular, there's one of these recent works from Dan Alistra's group at ISD Austria, Neuromagic, and they propose a method which you can prune up to 60% of the weights in a 175 billion parameter OPT and Bloom model with negligible performance loss on downstream tasks. I mean, their work targets inference time, but even then, like pruning 60% of the weights of such a big model does pave the way to, like, you know, run on like commodity hardware. And I think works like this will continue to push the frontier on like sparsity for language models. I mean, even our work, we were one of the few works I would say like actually look at pre-training with sparsity. And because we have the hardware to support it, I think it makes a lot of sense. And as we kind of build more and more intuition and findings, I think the ML community will like soon start to take notice of like how valuable sparsity can be for training.
You talk about the hardware supporting it. I think this is kind of the critical angle and why Cerebras were working on the sparsity research so closely. What's it like, I guess, doing this research on Cerebras hardware? Obviously, the background is to have good sparse performance, where if it's the weight is 0, you don't actually do the computation. You need that to be supported natively in hardware. GPUs don't support this natively in hardware. NVIDIA introduced a limited support for a very specific structured sparsity pattern in their last generation hardware, but it hasn't really seen much adoption. Tell us about like what's the hardware support like on Cerebras, and did you have to do anything special, or did you have to make the code more complicated in just exploring this area?
I think that's one of the beauties of the Cerebras hardware, because it's literally sparsity is literally just treated like another hyperparameter config to the end user. And like as an ML like researcher, running experiments on the CS2 with the Cerebras CS2 with sparsity, it's super easy, I think. And the fact that we have support for both static sparsity and dynamic sparse training, and we can actually translate those flop reduction to speed up, is pretty impressive. And this is what enabled us to do some of the research that we did in the paper at iClear, and some of the other sparsity work that we've also put out. And it wouldn't have been possible if like this without the capability of the CS2 to accelerate unstructured sparsity. And like I said, the sparsity, configuring sparsity for a model, like whether it's a language model, is super easy. In Cerebras like config, you can actually specify which layers you want to sparsify, how much sparsity you want to induce, and what type of sparsity, like static, dynamic.
What is the difference between static and dynamic? Why would you want one or the other?
Yeah, so I think, so maybe talk about static first. So static is literally just, you have a model at the start of initialization, at the start of training, and it's randomly initialized, hasn't taken any training steps, and you basically apply a sparsity mask for each of the layers that you want to sparsify. And this mask is basically set like sampled randomly on which weights to zero out from like a uniform distribution. And that mask now remains fixed, which is why we call it static. It's just fixed throughout the entire training period. But
you're just constantly plucking some things out.
Yeah, you just literally just randomly taking out weights. You don't even know if it's significant or not. And you hope for the best, I guess.
I see.
But the issue is, as you scale up to higher sparsity levels, this tends to the performance of these static sparse models tend to get worse and worse, because you're not deciding on the sparsity mask in a smart way, and the model doesn't necessarily adjust over time depending on the optimization process. So this is where dynamic sparse training comes in. Like dynamic sparse training, you still start with a randomly initialized model, but then every certain number of steps, you actually adjust the topology of the sparsity mask to make sure that you're actually training on the most important weights. And there's usually like a criteria that you use to drop and regrow these weights. And this tends to do a lot better than actually static sparse training, which kind of makes sense in hindsight, because as you're training a model at different points during training, certain weights are more important than others, which is something that static sparsity won't obviously capture.
Does dynamic sparsity then require extra computation to do the conditionals?
So with dynamic sparse training, you do have this like drop and regrow criteria. Each algorithm has its own sort of regrowth criteria. Typically, the drop criteria is still like magnitude based. You drop the lowest magnitude weights, and you keep the ones with the highest magnitude.
This process where you select what weights to drop, does that happen in sparse training, in static sparse training?
No,
Okay.
because there's really no point, right? Because
I mean, it
it
doesn't,
hasn't trained it yet, so
I see.
it just a randomly initialized weights, anyways. Yeah.
I see. But doesn't it cost you flops to, I imagine there's some code that's like, if your weight is below some threshold, then we null. Like, doesn't it cost you to run that
Uh,
compare instruction?
it's pretty insignificant. Like you're just running like a top K on the weights
Okay.
to, yeah. I the part that would actually contribute to some sort of overhead is the regrowth criteria. So depending on like what criteria you use, you may have to like still keep some set of the dense weights, right? It gets a little bit more complicated, but basically, like, for example, there's an algorithm called rigging the lottery, which is a short-term wriggle.
Yeah.
And it basically tries to dynamically adjust the sparse topology of every delta t steps.
Mm-hmm.
And the regrowth criteria relies on gradient information. And because you need the gradient information of all the weights in your matrix, as long as you're doing the recomputation like every delta t, then it's fine, and you just discard the unneeded or like unwanted dense gradients afterwards. But like that's the only overhead, and it doesn't contribute significantly to the overall sparse training, to the point where it like actually contributes more to the I mean, takes away from the actual flop reduction that you potentially or theoretically able to achieve.
Makes sense.
Yeah.
Cool. That's really great. I guess what is the next steps from your perspective on research? What are you excited to explore next after this?
Yeah, I think there's a multitude of things we've been exploring within our team. One of them is also another piece of work that we worked on called sparse isoflop transformations. This was co-authored with Shreyas, who's our lead research scientist, and Abe and Sean, our CTO. And we focused on actually using sparsity to improve the accuracy of a model. So there's this question that we tend to get asked by reviewers at conferences, or even in general, like people who are not non-sparsity researchers. Like, why should we even train a sparse network? Why can't we just train a dense network that's equivalent to the parameter capacity or representation capacity of the sparse network, right? And yeah, like, why don't we just train a smaller dense model? But from the start, instead of taking a big model and then sparsifying it. So I think this kind of motivated us to look in this direction at training a larger model and then sparsifying it, and then comparing it against like a flop equivalent dense model, right?
Right.
And what we found was that we can actually, the larger model has such like significantly more degrees of freedom during the optimization process to explore the optimization landscape, that when you can still induce sparsity, like dynamic sparsity, and take advantage of all that representational power, while being flop equivalent to the dense model. And in theory, since it's flop equivalent, you shouldn't have overhead in terms of training time, because the flops are the same as long as the hardware can support the accelerating the unstructured sparsity part. But we can actually improve, like, for example, a ResNet 18 model by 3.5% on ImageNet by making the ResNet 18 model wider, but then inducing, like, for example, 90% sparsity so that it's flop equivalent to the dense model. And we can improve it by 3.5%, which just by increasing the size of the model and inducing sparsity, which I think is which is pretty significant with just like one technique, because often you see in computer vision, people do all sorts of things like data augmentation.
3.5 is hard. Yeah. At this point.
Yeah, exactly. To get some, like, fraction of improvement on like ImageNet or something.
What is the difference in parameter count between the full sparse model and the dense model you're comparing to in this case? Like, how much bigger did you have to go to get this 3.5?
I guess you're asking the full dense model, or compare like the larger dense model versus the smaller dense model, or
the full sparse model versus the small dense model?
They're both the same parameter count.
Oh, I see. I guess what is the implied I guess, is there an equivalent number for the large sparse model if it were dense?
Oh yeah, so that we do compare against that as well. So we actually compared the large. Okay, so we had the larger dense model, which we compared against the sparsified version of that, and we actually see that the accuracy is still close to the larger dense model.
Yeah,
which is quite interesting, because you would expect that the larger dense model would like outperform the larger sparse model, right?
Yes.
But in fact, because we're using dynamic sparse training, we were actually able to show that we can still maintain that. We can still like be competitive with the larger dense model as well. I mean, it actually goes back to like what I discussed earlier, which was, as you scale the model size, you're more amenable to higher sparsity levels. And this is one of those things where now you have like this super large model, so much extra capacity that you can induce like 90% or whatever and still do well as the original dense model, without taking a performance hit. But I think like we still don't know what that upper bound, like what point do you have to hit to be able to like induce that level of sparsity and not affect the dense model. I think that's still like an open question. Like it kind of ties into like all these like scaling laws work. Like,
yeah,
how do we achieve like a Pareto frontier for sparse models that actually can match the dense model, right? Yeah.
Okay. Is there anything specific that you're working on next that will, I guess, that you're excited about?
I think one of the things is inspired by some of the work that has come out from like Christopher Wray's lab at Stanford, and on like something called reverse sparsification, which is basically doing like both sparse and dense training during the pre-training phase. So instead of doing the fully sparse training and then evaluating the model on the downstream task, we try to kind of mitigate the effects of like performance loss and representational power loss from sparse pre-training by doing this dense fine-tuning, right? But here we can actually try to improve the pre-trained model quality itself by doing like sparse to dense or dense to sparse, or maybe dense, sparse, dense. Like there could be a schedule that we can do where we still maintain the target flop reduction level, but we can get a much better pre-trained model, which in effect would do much better on the downstream tasks. So I think this is something that is going to be super interesting going forward. And the team and I have been like discussing many different avenues for exploring this research. And I think this is something that we'll see is like a promising direction for sparsity and making it more practical, I think.
Definitely.
Yeah.
That's very exciting. Vithu, thank you so much. This is exciting work, and we can't wait to see what new discoveries your team finds.
All right. Thanks so much, James. Great having you. Thanks for having me here. I think it's good that we're able to like, get our sparsity work out and like share with the community, because there's a lot of insights that we've gained at Cerebras from doing sparsity research that we'd love to share with the rest of the community. And I think we're always open to like collaborations with other researchers or industry partners who are also interested in doing sparsity research.
For sure. If you're working in this area, please don't hesitate to reach out to any of us. And I think our hardware is definitely a very ideal platform for you to do experiments.